Welcome back, everybody. This is the fifth final episode. Hopefully, you're learning something, having a little bit of fun with it. I believe it's section 3 and 4 were content heavy, a lot more serious for us. So this session is going to be the complete opposite, right? We're just going to talk. We're going to maybe give some stories. Jenna's going to pretend that she's become enlightened. And yes, there, the light's coming down on her. She's beaming. So we've taught and passed on. The pebble has been taken from the palm. You know, what do they call it? The student has become the master. So
I don't think I can get the whole fly chopstick thing though.
oh man, all right, wax on and wax off. Daniel said. So we're just going to talk. We're going to talk about what we've kind of learned so far. So we're going to do a little bit more, I guess, as just a discussion. I guess we put it down like Jenna was going to say what she learned, didn't learn, but let's just have a little more fun with it. You know, I'm in my more relaxed tone, you know. Although the sweatshirt's not that off the key. Let's talk. We'll go back and we'll actually close this up with some real stuff, right? So we'll talk about what we have going on. So we do have the red blood cells. That wasn't just for the fun of this or having a talking point. It helped there, but that's our heavy research, right? As Jenna knows.
Turn around and show Lauren right now doing this research.
So we're doing this based on looking at the red blood cells, using them not only as a actual research project, but as our personal thought to be a great biological control. As you have seen, we've mentioned that others, such as John Nolan, having red blood cell EVs for their controls. We do the exact same thing. The red blood cells play very nice in the sense that they don't have much in them. And our big project is looking at, we've published a paper on molecular beacons and within the red blood cell and other cell types and how they latch onto microRNAs and show particular microRNAs. You've seen that Alfonso plays with the different water so that we say we can set up a flow cytometer or a microscopy or something for small particles, right? Small particle detection is how I like to phrase it, instead of just extracellular vesicle flow. Because you can do algae, bacteria, viruses, exosomes, apoptotic bodies, liposomes, lipoproteins. I guess, Alfonso, it's just where your imagination will take you.
Yeah. In fact, there is a paper that I really like because it says microvesicles, exosomes, and friends. I really like that. Usually, that's the area that we are working on. Those very small things, and you cannot leave your imagination closed. Especially, you have to open it and think about a little bit outside of the box, especially in this area, right? Where
what were your detection limits lie, I would say? Like your thresholds and stuff that you can get down to for the size ranges?
We are working, or I am working with a friend of mine, because I think it's already 16 years working with him. So it's a friend of mine. And it's an Italian guy called Marco Monopoli. So they have a dye that's extremely bright. So he wanted to test how far he could go. Because as he said, I put this dye inside of a microscope and I have to put my sunglasses on. It's super bright. So, of course, if they show me something like that, I would be happy to try. So he was preparing some exosomes and some microvesicles. So he prepared 2 sets of samples from different cell lines. And then he brought those samples too. So we were playing with first with the scatter to see those particles and see that they are fluorescent. But also we have done exactly as John has done also yesterday and suggested, play with different thresholding. So in this case, if the fluorescence is so bright, let me see how low we could go. So we went there and we played with the threshold. We were able to go to far lower than 70 nanometers because he has checked those particles on the microscope. You can see that they were going as low as 80 counted by the nanosite. But also you can see some of my particles, my background was with negative, so they were not positive. So you can see even at the very clear drop down on those distributions, you can see down here even the negative particles that they haven't been labeled. So definitely we or background or noise or some fragments. So definitely I know that we were able to go far lower than 70.
Yeah, I think a lot of this is what we're learning is that, half jokingly is that you said you can go lower, and that's great. You stop to characterize lower and lower. And I've noticed even on ours as we're getting better at this, and you say, well, people's first question is, well, how low can you go? And as soon as you tell them that and go, well, can we go lower? So it's like, okay, well, at some point it has to stop. And it's just funny that you keep trying to find, right? Everybody wants the kind of magic, because it's the magic box, right? So they want the magic box to do everything. And, I think it was Howard Shapiro that called it the magic box, and you put sample in and the magic box spits out information. But there's a lot, as we've gone through with filters and APDs and PMTs and fluids and stuff, that goes into making the magic box give the answer. So it tests your mind, it tests what you can think of, and then it's being able to do it. So you can come up with anything, but can you do it? And I think the other thing I like is people say, well, why do you do these type of things? Well, one, it's fun, right? I get to talk to people that I like, and I get to put out some information and hopefully learn something myself, as I've said before. But the other reason is you think companies see this or other researchers, and so you get better ideas. You get people motivated to try to make the better mousetrap. So for me, right, it's almost like the sales pitch, right? It's like, hey, look what we can do, but if we could get some help, that'd be awesome. And you don't know, what is it? You don't know what you don't know is actually considered being smart. When you figured out what you don't know, you're great. And then it's the opposite when you just think you know it all. That's when you kind of get lost on these things. So I guess that's why you say, even though we do them, Alfonso's sitting there and he went through how he does his Cytoflex and all this wonderful information. You hear him also say, but I'm not an expert. I just I know what I know. And then I look for the people who can fill in the blanks of the things I don't know. I was fortunate enough, 10 years ago, 8 years ago, I can't remember the exact, to have someone come with me with a problem. And I've been trying to figure that problem out ever since. And we did some good things, but as the technology moves up, as the knowledge moves up, we learn it could have been a lot better. And so, you have some fun. We fake that we're, teaching Jenna and bringing her to the promised land. And so is the promised land, or is it the land of confusion? Either way, you're here. And so it's pretty awesome, right? To be able to do this. I've met more people now and done more collaborations. As a core manager, I wasn't necessarily doing major scientific projects, right? You're involved in certain things, you're giving advice, you're designing panels, but your day-to-day operations become making sure the instruments are good and that you're running the business appropriately. Since I started these projects and working with Anita, you mentioned Marco. I've gotten the pleasure of meeting, talking to Marco and whatnot. And you've talked to Anita, and he's given great ideas. We're part of grants. We're part of papers. I mean, this is so great for to be able to do as a core facility, to be able to write about these things, to be involved directly with the research, because sometimes people forget that, we're a service, but we started off and we're in this field of science. And we just happened to do our science using wonderful little toys. I think it was Susan. You know, we saw a picture and it reminded me of her, John Daly, that used to call Vasilis and I the boys with toys, because we'd always build all these things. We built something so that we could perforate red blood cells in order to try to get colors in them or microRNAs, and we had to put it in front of a laser. And we didn't know how to do it, so we came up. It was myself and an intern and Eric Zigan, and he had a Starbucks cup with a straw. We found a paper clip. We tied the tube to it and had the laser coming into the tube to perforate using, like, obviously, you know, it was basically laser poration. And my boss walked in and he goes, "Looks like a great idea. Not sure you can get a patent on that." So I guess the story is just to say, you know, with a slight bit of intuition and the ability and just the willingness to explore and do things like this, you can have so much fun. And it becomes more of a sandbox, right? Playing in the sandbox than it is a job. And I know, God, how many years has it been now, Alfonso? Yeah.
Just leave it like that.
And we've done multiple things together. We're highlighting some of the remote cytometry portions that has become part of the job. You know, the major focus of getting people's work done. We've been able to collaborate more on this extracellular vesicle stuff. Like I said, we have collaborators everywhere, not just our institutions. This is,
but also the interesting thing now that you're saying these collaborations. I do remember, and this was one of the things that has been canceled. Unfortunately, we were planning that you are here in Dublin at this point for running the summer school with me as well. And one of the key things here is the community itself, and that's true. You can ask anyone. You can ask questions, and it doesn't matter how dummy you are and how big the guru is, you can always ask. And that's incredible. And you can see that in those courses.
Yeah, I noticed
one time there was one user, we asked for the summer camp. Okay, come with samples and we can play with them. And we have different companies, each one with their own instruments. And we also have companies providing reagents. So I play with my user. Meanwhile, we were just playing around, and suddenly I see something weird. I said, "Look, I cannot find this." I went to another instrument. I said, "Could you show me how to run this?" And it was with, for instance, with Mark Cheatham, and say, "Hey, Mark, show me on your instrument how this works." I'm like, "Oh, there's something weird here." I say, "I know." What is that? And suddenly we had everyone from every single company together in the same instrument playing, and suddenly somebody said, "What if we add this die? Well, do you have this one?" "Yes, try." We were like kids in the middle of a toy center with everything that we wanted. It was fantastic. Yeah. At the end of that, we end up with a good with a good paper. It was about apoptosis and necrosis, but took us a good while to figure out what was that. And was part of the fun was this moment where you can see company applications, especially from many different companies, together with this dummy user that she was looking at us like, do they really know what they are doing? It was really fun. And that's the fun of this, I think.
Yeah, it's amazing. We've done the same thing, and you get multiple, like you said, multiple people from companies who are working together because we all fall into what's our original task, right? Is to promote science and to make better science. And so, you know, you put everything else aside and you're like, hey, how can we make this better? How can we help people get to their goals? And I know everybody started that stuff. I mean, I'm part of different working groups. They started the Slack channel that I shared with you, which is, you know, they're putting out great things like this, webinars and giving all kinds of information. You just post any question and there's a multitude of people who can give you a response. And it's great because you have, like I said, individuals who have different specialties. So, you're not just sitting there getting one person's opinion. Or obviously, if someone asks something specifically about, a cytometer, we may be able to answer that. If they ask how to, get into, me theory graphing and using, yeah, okay.
We can find a physicist.
Yeah, but there are individuals who that's what they do. And one of the funniest stories I can share here is, hopefully he doesn't get upset, is we were on a conference call with Edwin Vanderpool, and he's running the meeting. And at the end of the meeting, he goes, so are any of you cell biologists that I can talk to? He's like, I only deal in these small particle world. All my PhD thesis was on this. I have no idea about cell biology. And at first I was like, what? You have no idea about cell biology, but you're doing this stuff? And what? Oh, I guess it kind of makes sense because that's what we preach. That's how we started this. Change your mindset from cell biology. So I guess it's a great story in that it ties that right back from the first section of you've got someone and that's their life, right? He's a physicist. He's modeled all these things. Him and Josh have great programs for it. You mentioned the Rosetta. Jenna's been working a lot with Josh Welsh to try to come up with some sort of standardization, and his protocols and his program work very well for setting up the standard curve and getting that limit of detection out. So, and then Alfonso just said, hey, I want to know where my exosomes are. I want to label most of them. Oh, I met this guy who just happened to be doing a different project, needed a solution to a problem, and happened to solve my problem at the same time. Yeah. So the more you start getting involved in these things and meeting people, and like you said, Alfonso, we don't know it all. I mean, we ask questions. You go to a talk and you ask questions, right? You do this. I was asking Alfonso, oh, well, why do you do that? Some of it was to keep it going. Some of it was because I just don't know, right? It's not something I tried. And as I like to say, you meet some of the people that this has been their life's work. And as you start talking to them, you realize they've forgotten more about the subject than you will ever know. 5 minutes in the room and you're like, okay, hold on. Luckily, I'm not the smartest person, but I'm very good at being a sponge. Okay. I take it all in. Yoo-hoo.
A sponge.
And yeah, and I think this is why, we sit there and we give credit to certain people because they've taught us so much. Some people could say I'm just a guy or a gal there with Jenna with a machine. And as Alfonso was saying the other day, I got my thing and I'm moving filters around, and I joked and said, can you make it dance? And he went, da, da, da. And he's got his little one that he moves around, and it is. Our job is to make the thing dance, right? But a lot of the times we're not sure of the why, right? We want to know why. So this has given us the opportunity to move into the why. This is broaden our horizons. I mean, previously, I wouldn't care 2 bits about who uses an ultracentrifuge, a size exclusion chromatographer, density gradients. Yeah, okay, good for you. Bring me the sample, I'll run it, right? But like you said, with the apoptosis stuff, you look and you go, oh, this is so wrong. Help. And when you think about it, the only way to know if it's right or wrong is to start to fill in the blanks. And so by filling in the blanks, you start talking to the researchers, understanding their project, understanding what they're trying to do. And then you're able to get that solution for them. I'm sure you get the same thing, probably more than I do with your contacts, Alfonso. It is, you get a lot of, wow, you're great at connecting the dots. Because I always joke and say that my job, I'm like the bartender of the science world. People come to me, they sit down for a couple of hours while we sort or do their stuff, back when we could. They tell you stories, right? They tell you like this. They tell you about their life. They tell you about what their project is, their ups, their downs. And you start knowing. And then the next person comes in and starts talking to Jenna, and I go, whoa, wait, what? What'd you just say? Hey, there's a guy on the 4th floor who happens to have this, and he can't figure out why that's not doing that, and you can't figure out the thing he already figured out. You should talk to him.
Yeah.
And then all of a sudden you got this huge project, right? So you've got someone who has a HER2 new cell line with a, MUC1, and they start, hey, what? So the dendritic cells are being triggered by something. There's these little dudes all when we look under the microscope. Oh, okay. Well, this guy over here happens to have nothing but extracellular vesicles from breast cancer. And he's got them here, and he's realizing they direct things. And we found the red blood cells, as Anita says, the most precious cell of all, the red blood cell. That's why there's so many of them, because they're so important. But they tend to run a lot of things because they're one of the few, when they label them and track them, you put in them, they get rid of the EVs, and the EVs hone to the bone marrow. And they start triggering off other things, setting up. So they send out more, they make more, or they go to certain places. So if you're having, a heart attack, they start saying, need to go there. You've got something like a virus in your system. They say, hey, let's get everybody up and going. We need to send some signals over there. And while some people say, okay, well, they drop certain cargo, which gives the message, sometimes they just go to the site to give the message. They just show up and say, come over here.
This needs attention.
Yeah, and our whole job is to figure it out. So some of it, what used to be, I had 90% of people that came to me is, hey, can you give me a count and a size? And the flow is not always the greatest at doing. Okay. But now you can kind of get a size. You can get the concentrations. You can look at the cargo. Sometimes you don't even need the EV. You can just blow them up and look at the cargo inside, the microRNAs, the proteins. Some reports say they have DNA in these little guys. So you can definitely get really deep in this. The one thing I think we forgot in all this too is, if you say, well, how do I know it's an exosome and not a contaminant? People do detergent, right? Detergent lysis will affect exosomes. So if you use something, higher levels of the Triton X or an SDS or anything that is in the detergent line, that's a good way. So you'll see that published, and we'll plug it again because Alfonso had mentioned it many times. I believe John Nolan on maybe yesterday gave a talk. You can probably access that webinar if you didn't get to see it, based on the MyFlowSite EV standards, right? And being a part of that and dealing with that is what I want people to realize is our whole take-home message was, I think it was maybe Jennifer Jones that put it perfectly. We're not telling you this is what you have to do. We're telling you these are best practices, that if there's something in there that you just can't get done for whatever reason it is, well, it doesn't mean you can't publish a paper. We're just putting down, hey, in a perfect world, here's what would happen, right? But if it's not there, it's not there. And some of it too is just to give people like myself, like Alfonso, like Anita and Jennifer and Jenna and anybody else you can mention, guidelines when reviewing a paper. What should I be looking for? How do I keep this so that we have some legitimacy to it? Because reproducibility is a huge thing. It's very difficult in this field, right? To get those orthogonal methods. It's the word of the day, ding, 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 ding. We did it again, and to have that story. So I think I look at things all the time, and Alfonso, I've listened to you so many times. You, Peter O'Toole, you guys are great storytellers, okay? The science is there, the data is there, but why do I care? And you tell this such perfect stories, and they make so much sense, and they just are beautiful, and so it makes you pay attention. And in this field, the stories are coming together. You're getting better controls. As we started this, there are so many people in this field that have made so many mistakes that they're now able to direct you, right? So that instead of starting the marathon at mile 0, you're able to just jump in line somewhere around mile 20 and get to what works, and what might be prognostic, diagnostic, a biomarker, all those wonderful other buzzwords. So Jenna, and just going through this with learning from Alfonso, right? I'm going to ask you the question now, put you on the spot.
Okay. What's up?
What stood out the most to you that we don't do?
We definitely need to, we are ramping it up and starting to work on it more, but we do need to keep that red laser more in mind, because we have been solidly doing like the violet for a long time now. So to actually get that red laser in all the time and remember to do those filter swaps and have it set that way and continue on from there, and actually look more into that. And maybe we need to look back into some more filtration stuff with some of the PBS style things for our sample preparation. Just making sure on that end.
The interesting thing here, you mentioned now the red, and it's suddenly it was like processing things quickly, and probably some vendors will kill me for this, is that usually if you want to do some EV work, you want to have the violet laser and the blue laser. But some people, they just have the blue and the red. Why not to use the red laser, side scatter laser with the blue to identify some of the populations? You have seen already, you can use those ones. Of course, the violet, again, is giving you some extra stuff, much lower. But red and blue, a good combination as well to identify those populations if you don't have the violet. So yeah, because definitely it's an area to explore.
As you said, almost every survey you ever get from anyone, whether it's a company or just other individuals like us doing things, is, if you were to build an instrument, how many lasers do you need? What lasers do you need? How many different filters? Like, what is the minimalistic approach to it, though? Yeah, you say all of them, but you try to go into what's the minimum that you would need. And then it goes on to, what are the perfect controls? And it's like, well, if we knew the perfect controls, we wouldn't be telling you, we'd be doing it ourselves. Yeah, you'd already know because we'd be putting them out there. We've seen that. People have found some good controls and they've started marketing it, right? And there you go. And so, obviously there is no one perfect control. There's no one perfect stain. And some of it, a lot of these are based on you doing some preliminary legwork of, okay, well, what are the microRNAs that are involved here if I'm worried about cargo? What are the proteins that may be on the surface that are specifically targeted? There's a lot of cancer lines that have specific proteins that are on their surface that you can go after. And I've seen people just do that, label them out, and maybe tag that with an outer GFP. And then some people will use not even just the GFP properties, but I think Vera with her mouse leukemia virus has even done it in a way where you can put things out and then use an anti-GFP. And then get a bigger tag, a brighter tag, like a PE or something like that. And there's all kinds of different little options to purify these things and whatnot. And I guess the moral of my story for this, to tie it in, is if you're gonna look at all of this, is A, identify what you have, right? As far as what equipment is available to you, what resources do you have that are immediately available, and just build the protocol from there. And this is why I say the My Flow Cyte EV and any of the other, kind of position papers that are there are giving you those guidelines. Now, if they're saying, oh, well, there's NTA and DLS and pulse resistance, you may not have all that. You may not have access to cryo-EM and atomic force microscopy. And then things are there for you. Like you said, you set up the beads, Alfonso, you have your mega mixes and stuff, and you may be able to use those. And individuals, like Josh Welch, have freeware that you can use to start doing modeling and whatnot. I think the me modeling stuff is completely free. You just have to figure out how to use it. You can use Metvis and build your own, right? I'm definitely not smart enough for any of that. I mean, I'm relearning trig with my daughter in high school right now. So let's, that's the extent for me. But yeah, so you start the protocols, you figure out what you have, what you can do, and you just start to do it and make it again, make it a story, right?
Yeah.
Figure out what story you're trying to tell, figure out what the chapters of the story are, and then do that. Oh, look at this. We actually have some busy stuff. Jenna keeps running in and out. Yeah. During these times, I guess we have, science must go on somewhat.
One of the key things in science, and this is what I really like of cytometry field, is that people learn from mistakes, and they're not ashamed to even say what are those mistakes and which ones were the limitations at that time, and step back and change things. And I for instance, I was talking with Paul Robinson, and he was saying he was the first one publishing a multicolor analysis with 3 colors. But he doesn't want me to share the paper that he published because he said it's full of shit. So,
I don't have a beep button.
the paper itself is so full of mistakes, but at that time was perfect. So everything has to be a little bit relative. And I remember when I was in a workshop, and somebody was talking about the my theory, and suddenly I was looking at that. I was like, whoa, that makes sense, but at the same time make me worry. And suddenly display a series of instruments that they were really bad, and one of them was the one I was using, but was perfect, following the guidelines until that talk.
Yeah.
I'm like, oh, let me reconsider this. The funny thing is that we have done the triggering on fluorescence in the part in the hands-on part, exactly the same one that I was doing on my instruments, and those were my samples. And suddenly this crack on the my theory called Edwin Valdepor show up with his Rosetta beads, put them in, and said, look, this population that is really positive here for those markers, they're not EVs, they're your platelets. Your EVs are down here. So I was thinking, shit. That means that everything I've done with my user is in the bin. So I could be lucky, but definitely not. I was not lucky at all.
No, because
I've done a big piece of job, and that piece of job was really bad because I was following the guidelines, but I was not following the recommendations from Edwin. So I have to talk to my user and say, look, we need to restart this project. I don't want you to publish this thing, because then you will have to retract again, because I know now that it's wrong. So learning by mistakes makes you help and grow up. And I think that's a good story to keep moving things up.
All right. So I think this session was just us kind of like maybe blowing off some steam, right? Hopefully, again, you've learned some things, you've heard some good anecdotes and funny stories. Because I mean, we've had the same type thing. Luckily, for me, when I started this, I had Bruce and Barbara Fury, and basically they kind of guided it, because they started this things looking at platelets and platelet AVs, and for I think the moral of my story is try things. For those of you who have delved into the world of flow cytometry previously, moral of Alfonso's story that he just gave with Edwin and with J. Paul is, you tried something. You thought you had the right tools and information, but things have come a long way. You're right in the middle. You're kind of, I always say, well, we're like Watson and Crick, right? We're discovering things. You're right in the middle. You're down with this stuff in the flow cytometry world. If you've tried this and it didn't work, try again, right? Try a new tool with some new fancy features, and then basically reach out. So if you're still struggling, reach out to anybody, right? See if they have some suggestions, what the things that you've done right, the things that you could be doing better. We're not gonna say wrong, right? Nothing's wrong. So I mean, moral of the story is, again, keep saying moral of the story is, try, have fun. reach out to people who have had some successes, and any kind of channel you can get on, group that invites you in, do it. You're just going to learn. Go to your local flow cytometrist and ask. You may be surprised on how much they already know. More and more of us are getting that. Well, we're getting tasked with it, so we have to do it, right? So we have to figure it out. It's not just a select few. Some of us have been doing it longer, but I know, people that have just come in and they've had the benefit of having all of that previous experience at their fingertips. And so, they're coming right out the gate, doing it, publishing. So it's a good time to be doing this stuff. It all starts with a little idea. And
yeah, don't be scared. The first thing is don't be scared to try. I remember when I was trying to learn how to ride my bike, I fall a few times and I still jump in and keep trying, right? So that's the same story. It's not easy. It's scary sometimes, but if you don't try, you don't know. That's usually my phrase here. If we don't try, we don't know. And sometimes the best thing, as you said, John, is asking to another user. Usually the other thing is for students that they're starting up. Don't be scared to contradict to your boss. I know that will be terrible, but sometimes because you're so new, you're going to every single thing, trying to scratch everything. So you might at the end know more tricks than your own boss. And I always have the same fight with the users. Why you are having this marker with Fitzy? Oh, because my boss told me. Yeah. And it's because it's in the fridge. Yeah. But your boss has been doing his PhD like 20 years ago. That was the only dye available. Okay, now there are some others. And for this, it's better to put this together with these other things. So you have to be alert and have to try to get more things and try things. If your boss tells you no, some of us will do it for free, for fun. So, because we want to learn as well with you. So if you say we will have this, on this bunch of controls that you have to bring, put a couple of extra ones that will take you no time to prepare and will make the big difference for us. We want the controls, as John has mentioned. For instance, we want to make sure that we are working with EVs. There's detergent there, add detergent in.
And they go away.
Yeah. Don't do it, okay? You'll have troubles. But try those things that they are really, really simple and will make a big difference. And suddenly you have your own sample, will be your own control. I mentioned this about the dead cells. If we want to kill cells and we want to kill them, ethanol is your help. You have ethanol just there in the lab, add some ethanol, suddenly you can see your cells going from alive to death, and you will see how the changes. And again, open your mind to everything that you have on your instrument. Changes on fluorescence. Yeah, fluorescence is there, but changes on the scatter, as we have seen as well with the red and blue, is affected because of the staining. So changes on the scatter, changes on the fluorescence, changes on the number of events that you have, because you sort your sample and suddenly you reanalyze them afterwards, and my EVs are not there anymore because you have been playing with your high pressure. So they might end up on the tube. My EVs are not there. Yeah, but the cargo is there. The cargo is still there. You still have the proteins from your EVs. You still have your RNA from your EVs. They're destroyed. You cannot see them anymore, but they're still there. So why you don't try those things? Oh, a sorter didn't work. No, sorter work. Sorter sorts. So you have to change your mind a little bit and try to put as many controls as you can, because they will help us to interpret your data, and also will help us to show that you know what you're doing. Because at the end of the day, you can say, well, look, I have this control telling me this control telling me that. We have been talking about the PBS. Are you sure that it's not the antibodies? Yeah, we run the PBS with your antibodies, and it's still the same thing. But that could be because you have, who knows, the dye floating around and is coming. Okay, we ran the dye as well. There's not an antibody. You can see it's still the same baseline. And that could be your cells. We run the cells. They are up here. That could be that you're in the wrong settings. We have our internal control. So you put all those controls. So definitely the only thing that could happen is that we have our cells. And what about the tubes? Oh, we have tried different tubes as well. So,
Yeah.
so as many things as you try to prove that your population is there and is consistently there, better for you. So that's usually the thing that we are talking with the users. Help us to understand what you want, because more information that we get, more things and we can think around that, more experiments we can play around, or even as John has pointed out, we know somebody that knows somebody that has done this before. So we can ask.
The old phrase, I know a guy.
Let me get back to you on that.
Yeah. So, all right. So we'll wrap this session up too. But I guess to kind of summarize, and correct me if I'm wrong, what Alfonso's been able to kind of just iterate there is, it makes no sense you wouldn't buy a book that only had the introduction and the ending, right? You basically want to make sure that you have done all the chapters in between and you have everything done. And so a lot of people talk to others to get that information. And so it makes a perfect, like I said, you're making a story and you want every chapter of the story to be there. So we've learned a lot. I do want to put in we are definitely not 100% expert. The information put here is things that have worked for us. And this was never meant to be 100% perfect information. This was meant to be more of a fun, joyous thing and pass some time for everybody. As my CAO here and my boss, Dr. Weller, always like to say, this is a perfect time to think about these things, to come up with new experiments, and really, get going for your next grants and start thinking about future manuscripts. So there will be a link to the live session, I believe, at the end of this one, in which will be questions, answers again. Put all those in there. It can be as simple as, why are you guys so strange? Although that might be a very long session.
I think we'll run out of time before we finish that one.
Yeah. So, and hopefully by then we'll have some more research done that we can share with you at that live event. So, again, keep thinking it out, keep doing, some new things. Come find the wonderful people, read your MyFlow site, join the Slack channel that exists for the EV working group. I think if you type in EV working group flow cytometry, it'll get you there. Or if you look up Josh Welsh or Edward Vanderpool, Andre, if I hack his last name, Gorgons, he set up the Slack channel. Brilliant idea. So thank you all once again. Thank you, Alfonso and Jenna, for taking the time. Jenna, thanks for playing the very naive individual. And your acting is incredible.
Hey, I'm still learning, so this is fine. I'm always happy for the refresher.
Me too. Thanks for the people behind the scenes. I keep calling him Martin Scorsese. And we're going to sign off. Stay safe, everyone. Thank you.
Thank you.
Bye.